Hello, everyone. Thank you, and welcome to this exciting talk about the future of progressive lenses. Today, when you go to an optician, there are basically two ways to get your vision tested. A traditional vision test made using a phoropter or a trial frame, and a more advanced biometric vision test made using a device like the DNI scanner. The output from a traditional vision test typically comprises of 4 parameters, while the measurements carried out by the DNI scanner are used to determine more than 7,000 data points and over 80 parameters in the eye. As lens manufacturers, we use this information as input in the lens manufacturing process to determine how the lens can be crafted in the most precise way possible. What we've learned at Rodenstock is that the more we determine about the biometrics of the individual eye, the more precise progressive lenses we can manufacture. Actually, applying this kind of precision to lens manufacturing results in up to 40% sharper vision at near and intermediate distances, and an 8.5 degrees wider field of sharp vision at near. But today, not all opticians use a DNI scanner. In these cases, the only input lens manufacturers often have to work with is the standard prescription values. They have no information about the biometrics of the individual eye, and this affects how precisely the lens can be tailored to the needs of each spectacle wearer. So, here at Rodenstock, we asked ourselves how we could provide people with sharper vision, even with lenses made using just the standard prescription values. With this goal in mind, we started analyzing the more than 500,000 individual biometric eye scans that we've collected from producing biometric intelligent glasses. What if we could find patterns and correlations in this data that we could use to transform the standard prescription values into more valuable information about the biometrics of the individual eye? To identify the biometric parameters that would be most important to gain information about, we turn to the anatomy of the eye and the structure of the vision system. We know that as light travels through the eye, it is refracted to hit fovea centralis and form a sharp image on the retina. Each of the elements that light passes through plays a central role in forming vision. Since they have different refractive indexes, every one of them has to be determined precisely. From the parameters that influence how light is refracted in the eye, we began by looking at the eye length. Today, most lens manufacturers assume that all people have the same eye length of approximately 24 millimeters. But in reality, we know this isn't true. Eye length can actually vary by up to 10 millimeters from person to person, and this means their eyes refract light differently. Let's look at a sample of test persons. If we assume they all have the same eye length of 24 millimeters, it looks like this. With the DNI scanner, we can determine the actual eye length of our test persons. When we put these determined DNI scanner values into a graph, the individual eye length values distribute as follows. Here, we can see how much eye length deviates from the standard assumption, the line that goes here. This raised the question: how can we use our biometric knowledge to determine the length of each eye more precisely? The answer lay in our immense biometric dataset of more than 500,000 individual biometric eye scans. Using statistical analysis, we started looking at eye length in relation to other eye parameters. Here, we identified a relationship between eye length and sphere, one of the standard prescription values that are always available to lens manufacturers when a standard vision test is conducted. When we measure the prescriptions for our test persons, we see a clear relationship between eye length and sphere. With this correlation, we are able to identify a new, more precise norm for determining individual eye length without actually scanning it. In fact, this new norm allows us to determine approximate eye length just from knowing the spherical power of the eye in question. But, as many of you might already know, the DNI scanner does not directly measure eye length. So how can we actually determine eye length using D&I measurements? To explore this, we've reached out to Dr. Annie Seidemann, Senior Manager in the Optics Research Department at Rodenstock. We asked her to explain the science behind how we determine individual eye length by using D&I parameters as input.
Yes, thank you. So, we started by conducting 2 scientific studies on biometric measurements in collaboration with the University of Tübingen and the University of Applied Sciences in Munich. We measured the exact actual eye length and a number of other eye parameters of 137 persons using a biometer, the lens star. In addition to actual eye length, we determined the refraction of the eye along with corneal topography, anterior chamber depth, and crystalline lens power. We determined these parameters because they are in fact related to eye length. So, when we scan different parameters in the eye, such as corneal topography and anterior chamber depth with the D&I scanner, we gain information about a lot of different parameters that tell us something about eye length. Looking at the power of the eye, for example, it's well known that hyperopic eyes are shorter, while myopic eyes are longer. This means that when we know the power of the individual eye, we can actually already calculate the length of the eye within a 3.5 millimeter interval. When we add the spherical power of the cornea to the calculation, the calculated interval is reduced to less than 2 millimeters. Finally, when we then add multiple other parameters, such as the anterior chamber depth, the spherical aberration and the cornea, and many more to the calculation, we are able to determine the exact value of 27.1 millimeter. Ultimately, we can include this exact eye length in the lens calculation and graph the lens more precisely, ensuring that it fits the individual perfectly.
Thank you, Dr. Seidemann, for enlightening us. Moving on from eye length, the next central eye component we need to look at is the cornea. The primary function of the cornea is to refract the light and focus it on the retina. On average, it takes approximately 63 diopters of refractive power to focus rays of light entering the eye onto the retina. The cornea holds about 43 diopters, or almost 70% of the total refractive power of the eye. This is what makes it an important visual component. Because of this, we again asked ourselves, how can we unfold the standard prescription values to gain valuable biometric data about the individual cornea? The most important thing to determine when it comes to the cornea is astigmatism. Astigmatism is an irregularly shaped lens or cornea. These irregularities have significant influence on how light is refracted within the eye. Astigmatism can exist in any meridian of the cornea, both in horizontal and vertical angles, as well as in oblique angles. This makes it important to determine the astigmatism of each cornea because it allows lens manufacturers to optimize the lens to correct the corneal astigmatism, ultimately adapting the lens better and creating clearer vision. In spite of this, most lens manufacturers use a standard value for corneal astigmatic power. They assume that the eye has a corneal astigmatic power of 0, and this means the lens is not corrected to support corneal irregularities. Following this assumption, when put into a graph, both ortho and oblique corneal astigmatic power would look like this for our test persons. However, when we measure with the D&I scanner, we can see how the values are distributed in reality as corneal astigmatic power differs between individuals. So how do we then calculate the corneal astigmatic power of an eye just from the standard prescription values? We've asked Dr. Gregor Esser, Director of Optics Research and Development at Rodenstock, to show us how calculations make it possible.
Yes, thank you. So, from any standard vision test, we gain a minimum input of 4 prescription values, which we can use to optimize the lens in the manufacturing process. But to be able to unfold these standard prescription values and optimize the lens towards the actual biometrics of the individual eye, we needed to convert the prescription values into a format that is viable to use for statistical analysis. More specifically, we needed to convert our traditional way of describing the prescription of the eye as cylinder and axis value into power vector terms to describe the prescription values in a way that is mathematically different. To do this, we use the following formulas in which the traditional prescription values are converted into power vector terms. With the identified power vector terms J0 and J45, we can identify a relationship between the astigmatism of the whole eye and the astigmatic power of the cornea. With these correlations, we can define two new norms for calculating the astigmatic power of the cornea when crafting lenses.
Thank you, Dr. Esser. Besides the astigmatism of the cornea, to our own surprise, we found in our biometric data analysis that there's a correlation between pupillary distance and the spherical power of the cornea. The spherical power of the cornea makes up a significant part of the spherical power of the eye. An irregularly shaped cornea has a significant influence on how light is refracted. The greater the curvature of the cornea, the more the cornea's converging power increases. Going back to our test persons, we can use the DNI scanner to measure the spherical power of the individual cornea. Here, we can see just how much spherical power differs from eye to eye. Using our biometric data pool, we analyzed the correlation between the spherical power of the cornea and pupillary distance. Here, we could see the clear correlation that exists between the spherical power of the cornea and pupillary distance. Using this correlation, we are able to create a new norm for calculating the cornea's spherical power. Another eye component that's important to consider is the pupil and its size in different conditions. The pupil limits the light rays entering the eye and controls the amount of light hitting the retina. As we go through the day, our pupils constantly contract and dilate as they adapt to different light conditions and object distances. In fact, the pupil can change from less than 2 millimeters in diameter in bright light conditions to 8 millimeters in dark conditions. And when we look at objects at near, the pupil contracts to support the process of creating a sharp image of the object. This constant adaptation of the pupil's size influences the image that is formed on the retina. That's why knowing the size of the pupil in different light conditions and at different object distances is important when manufacturing the lens. Because the pupil is so important to our vision, we've also used our biometric data to find a more precise way to identify pupil radius in lens calculation when exact DNI measurements of the parameter are unavailable. It's well known that a relationship exists between addition and pupil radius. Using this correlation, we can calculate the pupil radius of each eye using just the addition of the individual eye. This allows us to form a new, more precise norm for calculating individual pupil radius. Moving on from pupil radius, the fifth component vital to determine is the shape and position of the crystalline lens. The crystalline lens holds a third of the refractive power of the eye. It refracts rays of light onto the retina and allows our eyes to focus on objects placed at near and far distances. When we focus on an object in our near field of vision, the muscles around the lens contract, making the lens thicker and rounder while changing its refractive power. When we focus on an object at a far distance, the lens flattens, decreasing its optical power. Due to its central role in the vision system, accounting for the crystalline lens accommodation ability is critical when creating the lens, especially considering the effects of presbyopia, which is projected to affect 1.9 billion people globally by 2050. Another correlation prevalent in our biometric data was the direct correlation between addition and the thickness of the crystalline lens. As the thickness influences the refractive power of the lens and thereby the eye's ability to focus at near and far object distances, the correlation gives us valuable biometric input for the lens calculation process. With this correlation, we can make a final new lens calculation norm that will improve the way we account for the accommodation ability of the crystalline lens when manufacturing progressive lenses. But how can we use these new norms to take the next step in lens calculation and improve the way we create progressive lenses when exact D&I scanner measurements are not available? To be able to combine the correlations and use them to build a biometric eye model, we needed to develop an advanced mathematical setup based on a series of algorithms. We've asked Dr. Dietmar Utenweiler, Head of R&D and Strategic Marketing Lenses at Rodenstock, to explain how we overcame this challenge.
Thank you. Now, to build a complete biometric eye model, we need to utilize the precision from many different correlations and look at the correlation values in a multidimensional environment. But combining all these correlations is a highly complex mathematical process that requires immense calculation power. Therefore, we started exploring how we could solve the task and implement our data findings in lens calculation on a broad scale. And the answer was artificial intelligence. With artificial intelligence, we were able to analyze many different correlations at a time and draw a multidimensional correlation line for the individual eye. Finally, from all these correlation lines, it's possible for us to build an approximate biometric eye model that is based on approximate individual eye values obtained from the multidimensional correlation analysis as just described.
Thank you, Dr. Utenweiler. Now, this illustrates how artificial intelligence has the potential to raise the bar in progressive lens manufacturing. As illustrated by Rodenstock's biometric intelligent glasses, the vision benefits of manufacturing lenses using an exact biometric eye model are still unparalleled. But building an exact biometric model for the eye requires exact individual measurements made with the D&I scanner. With artificial intelligence, we have the opportunity to raise the standard within progressive lenses. With AI technology, we can make it possible to include approximate biometric measurements in the calculation of the lens. Thereby, we are creating a new norm within progressive lens manufacturing, a new norm that we are excited to tell you more about at OPTI 2022 as we continue our work to bring AI and biometric data into lens calculation on a broad scale. Thank you.